We've left the biggest questions of them all for this fifth and last lecture, the origin of the universe itself. What I'm going to do today is to tell you the story of the Big Bang. We discussed it briefly in the last lecture, but now we're going to do it in more detail. What we're going to find by the end of this lecture is that there are 4 fundamental problems about our universe which we have to try to solve. 25 or even 10 years ago, we could barely have asked the questions, far less even suggest answers. But now, through many very intriguing developments in particle physics, we've got possible solutions to even these 4 great questions. Once again, we're going to go to the very limit of present understanding, and there are going to be many more questions than answers at the end of the lecture. But again, I cannot leave you without trying to show exactly what the current state of these major problems is. What we're hoping to do is to get a deeper understanding of fundamental forces in nature. So how are we going to do this journey? We're going to go on a journey back in time from our present day to the very earliest stages of the universe. So let's begin with the story of the Big Bang. Now, we've already met 2 of the key facts about the universe which we will need in order to start our journey. The first is the fact that the galaxies are expanding away from our own galaxy. This is Hubble's great discovery, in which he found that the velocity of a galaxy away from us is proportional to its distance from us. This is Hubble's famous law. The second important fact is the fact that the universe looks the same in all directions. And if we look in particular at the microwave background radiation, the radiation which we will show is the remnant of the hot early phases of the Big Bang, we find it's fantastically uniform. Here's a picture showing the whole of the sky with the plane of the Milky Way along the center, the north galactic pole looking out of the plane in this direction, looking below the plane in this direction. And if I put my hand across our own galaxy, you can see very few ripples at all on the distribution. And the amazing thing is that the size of these ripples is no more than about 1/10,000th of the total intensity of the radiation. In other words, this radiation is fantastically smooth, almost certainly better than 1 part in 30,000 smooth. Now, we can argue very convincingly that these 2 facts tell us that our universe is expanding uniformly. We can think of the distribution of galaxies being put on the surface of this sphere and the whole distribution expanding. Now, that's great, but what about the dynamics of the universe? In other words, will it carry on as expanding as it is now? Will it slow down? Will it accelerate? What will happen to the universe? Well, we can build a very simple model to get the exact answers for what we expect. We can imagine that this is a little bit of universe, a spherical bit of universe, and that our galaxy is at the center, in the very center of this sphere. And then, as the sphere expands, we would see the universe expanding about us. Now, we can then ask, what would be the forces on a little galaxy sitting at the edge of this sphere about us? Now, we can see on this picture here what we expect. Here's this sphere centered on our galaxy. And of course, the universe is expanding, and so the edge of this sphere is moving away from us. But of course, all this expansion is being decelerated by the force of gravity, which is trying to pull the universe together. And that is what our models of the universe are about. It's a competition between the fact that the universe is expanding and that it is being retarded by the effect of its own self-gravity. Now, you can see intuitively what this must mean. If there's a great deal of mass within this sphere, then there will be sufficient gravity to stop the expansion, and the universe will collapse back again to a dense phase. If there's not a lot of mass in this sphere, then the universe will expand out to infinity, and we will have a never-expanding universe. Now, what I'm going to do is to show the analogy between rocket ships or cannonballs escaping from the surface of the Earth and our expanding universe. And I'm going to need a computer expert today. Now, who would like to help me today? Let me see. Where are we going? Would you like to come and help me? What's your name?
Olivia.
Olivia, good. Come round here. Are you good at firing cannons?
Not that good.
Not that good. Let's see. You come round here, right? Now, you see this picture here? What we've got on the screen here is a cannon, right? And we're going to set off cannonballs at different velocities from that cannon, right? Now, I'd like you first of all then to put in, say, 1 plus 1, and then press enter and see what happens. Just that one there. Oops. Golly, what was that? Did you see that? Now, that cannonball was going off at a velocity greater than the escape velocity, and so it escaped right outside the Earth's gravity, and it's gone away, right? Now, let's try another cannonball. Let's put in nothing, right? And then press the return button there. Well, that cannonball went off with escape velocity. It didn't go quite so fast, and it will have eventually got to infinity, but will have almost stopped there. Now, let's put one that doesn't have the escape velocity. Now, if you put in minus 1 and press return again there, let's see what happens. It never made it. Thank you very much. That was very nice, Olivia. Let me just show you the trajectories of these cannonballs again. There's the one that doesn't escape, there's the one that just escapes, and there's the one that has got velocity greater than the escape velocity. And this is showing absolutely precisely not only how cannonballs escape from the Earth, but also how the universe itself expands. Because if I now put the axes on this diagram, bang, bang, bang again, what we find is absolutely precisely the dynamics of the universe. Because we've got now along the bottom axis time running from the Big Bang forwards, and we've got the separation between any two galaxies expanding with the universe up this axis. It's just telling you the relative size of the universe as a function of time. And if you've got dense model universes, they will collapse back to the Big Crunch. If the universe has got its own escape velocity, then it will go along this curve and end up with 0 velocity when it just gets to infinity. Or if it's got very low density, then it will escape along this line and will end up infinity with a finite velocity. And that's all there is to the models of the universe. It's no more than cannonballs trying to escape from the Earth. Now, there's one key concept that we're going to use over and over again, and that is the idea of the critical density in the universe. You'll see that on this last slide, we had the 3 model universes, and this one, which just had the escape velocity, has got a very special density, which we will call the critical density. It is that model which divides those models which will expand forever from those which fall back on themselves again. This critical density amounts to only about 1 hydrogen atom per meter cubed throughout the whole of the universe. So it's a very, very low density indeed. Now, let's look at something completely different, but which will prove crucial to the latter part of the lecture. Now, Einstein had one very great realization, and that is that matter bends the geometry of space and time. Matter bends space. And it's a very fundamental realization. And so what it means is, when we've got matter in the universe, there's no reason why our geometry should necessarily be the Euclidean geometry that we're very familiar with. So let's have a quick introduction to non-Euclidean geometry. If this sounds horrible, don't worry, it's actually all very simple. Now, I need another helper to help me with this particular experiment. Would you like to come and help me? What's your name?
Rachel.
Right, Rachel. Are you good at geometry?
I'm okay.
You're okay, that's great, super, right. Now, you'll recognize here, we've got a flat sheet here, and we've drawn a rather beautiful triangle with all the angles equal, right? Now, I'd like you to take this triangle and place it on that triangle and confirm that it actually fits.
Yeah.
Does it fit?
Yes.
Absolutely perfectly. Right, okay. Now, what we're going to do now is to change from flat space to curved space. Okay? Bryson, let's go. It's quite a good balloon, right? And it keeps going and going and going and going. Now we've changed from flat space to curved space. Now, why don't you take this and go around that side, and we'll just compare the angles now to see if they're the same. So if we lay that along there, now what's happened?
That's gone bigger than that.
Exactly. You see that the angles have all expanded on the triangle. And that's bad news, isn't it? Because what it means is that the angles of the triangle no longer add up to 180 degrees. Are you worried?
Yes.
Oh dear, right. Thank you very much. That was a super demonstration. Because, you see, there's no reason why, when we look at the universe on the very large scale, the geometry of space might not be spherical like this or flat. Now, in our models of the universe, Einstein tells us there's a very close relation between the geometry of space and the amount of mass there is in the universe. And in fact, in the models of the universe we've just built, ones which are completely uniform, there are only three possible geometries. There is the spherical geometry that we have here, in which the angles of the triangle end up being greater than 180 degrees. There's the flat space here, just a flat sheet of paper, where the angles of a triangle equal 180 degrees. And then there's one other, which is the opposite of this one, which looks something like a saddle. Now, this is very difficult to actually draw, but a saddle makes a beautiful point of what the geometry looks like. You see, you've got a curvature in this direction, and the opposite curvature going in that direction. And if you now draw a triangle on a saddle, try this next time you go riding. If you draw a triangle on a saddle, you will find the sum of the angles of a triangle are less than 180 degrees. These are the three sorts of geometry that we are allowed in our uniform models of the universe. Thank you. Now, we will need this result later in one very important point in the argument. It turns out that in these models of the universe that we've built, there's this beautiful relationship between their dynamics, in the sense of the way they expand, their density, and their geometry. So it is only in the critical density, the model in which the universe has its own escape velocity, in the sense of escaping from itself, it's only in that model that we find that the geometry is flat. If the density is greater than the critical density, we find the universe will collapse on itself again, but the geometry is spherical, as here. If the universe has got density less than the critical density, then it turns out that the geometry of the universe is hyperbolic, just like the saddle here. Now, what do I mean by the geometry of the universe? Well, it's very simple. You see, if I was going to draw a triangle from us here in the Royal Institution out to one quasar, and then across to another quasar, and back again, and we worked out the sum of the angles of a triangle, then it will not necessarily be 180 degrees. Everything's all right within the Royal Institution, and don't start worrying about having a curvature of space within a sheet of paper. That never happens. It's only on the scale of the universe that the geometry may well be curved. Now, there's one other very interesting relationship, and that is there's a relationship between the density of the universe and its deceleration. In other words, in all of these models that we've looked at, the universe is decelerating, and that's entirely due to the matter which is within the sphere. So we can do a great test of Einstein's theory of general relativity on the scale of the universe itself if we can show that the deceleration of the universe is entirely due to the matter within it. This turns out to be a horribly difficult experiment to do, because we don't know the density of the universe very accurately, and it's even more difficult to measure the rate at which it's decelerating. Let's look first of all then at the density of the universe. Now, this red weight here is going to represent the critical density of the universe, and I will put it in that scale pan there. How much matter do we know there is in the universe? Well, in visible matter, we know there's about 1/50th of that mass, which certainly isn't enough to close the universe. But you will remember that in our last lecture we said there was a great deal of dark matter present, at least a factor of 10 more in galaxies and in clusters of galaxies. And when we look on even larger scales, there may be even more matter present, and we can pop that in the scales too. But we're not at all certain whether we can get up to the critical density of the universe or not. Measuring the deceleration is even more difficult. But what we can say is that within a factor of about 10, we've got good agreement between the deceleration of the universe and its density. Now, that may sound pretty bad if you're used to laboratory physics, but in cosmology, if you're within a factor of 10 on anything, you've done very well. So we really should be quite pleased. Now, this fact that we're roughly within a factor of 10 of the escape velocity of the universe leads to one of the first big problems we have to solve. Now, we want to go back to this idea of the escape velocity again and ask what the velocity of the universe is relative to its escape velocity. And I'm going to do this by a computer simulation, and I need another real computer expert from the audience. Who would like to help me this time? Right. Would you like to come and help me? What's your name?
Daniel.
Hi, Daniel. Right. Come here. Now, I've got to explain this diagram first, and then you've got to be the computer operator to drive this spaceship. What we're going to show is how it is that spaceship escaped from the Earth. All right?
Yeah.
We've got the Earth here, and we've got a spaceship here, which is going to take off. All right? Now, at the surface of the Earth, we're going to give it a certain velocity, and we're going to describe that in terms of the escape velocity, all right? And then we're going to ask, how does the velocity when the spaceship gets away from the Earth compare with the escape velocity when it's further out? Now, see, there's an important point. When we move away from the Earth, the escape velocity gets smaller, and also the velocity of the rocket gets smaller. But how does the ratio of the two change? Okay? So let's put in 2 first of all, and then return. So if you just put 2 and then press return, we'll see what happens. There goes the rocket. Lovely. Okay? Now let's see what happened. Now what's happened, the rocket here has got twice the escape velocity, and then as it moves further and further away from Earth, then the ratio of the velocity to the local escape velocity gets bigger and bigger and bigger and bigger, to huge values. Okay? Now let's put in small values. Let's put 1.1. Okay? 1. You can try that point. 1. Return. Now again, it's very close to the escape velocity on Earth, but very soon it picks up velocity and zooms away. Let's try a really small number. 1.0001. Okay? And return. Now there goes the rocket again. Almost with the escape velocity, but eventually what happens?
It's up.
It goes up. Thank you very much, Dan. That's great. Now, that is a very subtle experiment, because, you see, what it's showing us is that even if we start off with velocities very close to the escape velocity, eventually the rocket ship, far away from where it started, will start to get a very large velocity relative to the escape velocity at that time. And now this is what the problem is for the universe. You see, the universe has expanded by an absolutely enormous factor from its beginning. And yet now, we're still within a factor of 10 of our escape velocity. So what that means is that this curve up here must still be very, very close to this axis down here, despite the fact that the universe has expanded by enormous amounts since its beginning. And therefore, the universe must have started off with almost exactly its escape velocity. In other words, even if it deviated very, very slightly from its own escape velocity, then we would be miles and miles away from our own escape velocity now. And this is an enormous problem, because, you see, there's nothing in our models of the universe to tell us why the universe has to start off with exactly the critical velocity. We could choose any density of the universe we wish, because there's nothing in our equations to tell us where we should start. And so we would either have universes which are very much younger or very much older than they are now. Why has the universe selected the exact critical density for its evolution? Now, there's a bit of a problem here, because, you see, we've only got one universe to look at. You know, we're stuck with it. We can't go out and ask someone else what's happened in your universe, because we've already done everything is accessible to us. And there's many interesting questions about the philosophy of cosmology, but I'm not interested in that. I'm simply interested in the physical fact that our universe must have started off remarkably close to the critical value. Now, so much for the matter. What about the radiation in the universe? Well, we've already talked about the microwave background radiation, and I'm showing you again here this beautiful spectrum of the microwave background radiation. The spectrum was taken by the Cosmic Background Explorer within the last year, and it shows that the radiation has this almost perfect black body form. Now, we're going to show you what we mean by black body radiation by doing a rather simple demonstration in which we're going to get a carbon arc at a a temperature of about 5,000 degrees Kelvin, and we're going to take its spectrum just to show you an example of a black body. Right, Bryson, let's switch on the machine. And now what we're going to do, once we've got that lined, we're going to put in a prism to disperse the radiation into its various components. And you can see beautifully on the screen there, the light is being dispersed into red, yellow, green, blue. Now, if you look on the pointer at the bottom, I'm now going to measure the intensity of the light by this horn here. There's a detector in here, and I will now move it across so that you can see this will trace out the intensity spectrum of the black body curve. Here we go. Now, there's not much energy in the blue part of the spectrum, but as I come across to green, red, here we come, there comes the energy, lots of energy in the infrared, and then when you go to the far infrared, it comes down again. It's tracing out exactly a black body curve. Thank you. The temperature of the arc lamp was about 5,000 degrees, so let me put this through this program, which shows what will happen if I've got a black body with that temperature. And this is exactly what we saw on that demonstration. You'll see here is the spectrum of a body at 5,000 degrees. There's little energy in the blue and green region, and then it comes strong in the red and even stronger in the infrared, and then it dies away when we go beyond that wavelength. Now, what is the significance then of black body radiation? Well, it's radiation which has been in thermal equilibrium with its surroundings. In other words, we only get this very special thermal spectrum if the radiation and the matter have been in very strong thermal contact so that everything is in equilibrium. Every emission is balanced by an absorption. It is what we call thermodynamic equilibrium. So this must have happened to that radiation at some stage. Now, in the case of the microwave background radiation, the temperature of that beautiful Planck spectrum is only 2.736 degrees Kelvin above absolute zero. And so it's very, very cold. Now, what we've got to ask then is what happens to that beautiful black body curve when we let the universe expand, or if we go on our journey back in time, if we compress it back in time. Now, we've already met this effect in the last lecture. You'll remember that there's effect of stretching of wavelengths when we observe distant objects. In other words, there's this phenomenon of redshift whereby a distant galaxy emits some light and we receive it with a much longer wavelength. It's exactly the Doppler effect which we hear when we whirl a whistle around our head or when a police car is rushing away from us. We hear a lower tone than we would if the police car were at rest. Now, exactly the same thing happens to radiation originating far from us in the universe. But I want to demonstrate exactly that same in a slightly different way. We've made another little computer program where we've got a little wave here bouncing back and forward in a sphere. And you'll notice it's got a rather short wavelength. Now, what happens in the expanding universe is that the wavelength begins to stretch as the universe expands. And so what I'll do, I'll just now set this program going to make the universe expand and watch what happens to the wavelength of the radiation. Here we go. Can you see what's happening to the wave? What's happening? It's exactly right. The wavelength is stretching. And the wavelength of the radiation is just expanding exactly proportional to the size of the sphere. This is exactly what happens in the universe. As the universe expands, the wavelength increases, and it goes from what started as a blue wave to what we're now representing as we get to the end of the simulation as a red wave. It's simply demonstrating another way of thinking about the phenomenon of red shift. Now, this is a remarkable phenomenon, but it occurs very generally in all models of the universe. And now we've got to ask, what happens then to our microwave background radiation when we take it into the past? Well, exactly what we saw on the screen will occur, but going backwards. We will squash the wavelength of the radiation, and therefore it will get hotter. You may remember from our first lecture this very strong relationship between wavelength and temperature. When we squash the wavelength, the temperature goes up. And in fact, in the universe, the temperature is just inversely proportional to the spacing between the galaxies. Now, it's a beautiful result, and it's terribly important, and I want to show you in detail how this works on this rather complicated but very important picture. What we're showing here is the temperature of the radiation in the universe going from about 1 degree Kelvin here to 1 billion degrees Kelvin here. And along this axis, we've got the factor by which we squash the universe backwards in time. So here is the radiation here at about 3 degrees Kelvin at the present time. Now, if we squash the universe by a factor of 1,500, then we get up to a temperature of about 4,000 degrees. And when we get to that temperature, then the radiation is so energetic that it's able to split up hydrogen into its protons and electrons. The temperature keeps on increasing as we go back in time, and if we squash the universe by a factor of 300 million, the temperature will get up to about 1 billion degrees Kelvin, which is pretty hot. And in fact, at that temperature, it's so high that the radiation here is now shifted to gamma ray energies, and the gamma rays are so energetic that they can split up the nuclei of atoms. What that means is that when we go to even earlier times, even the nuclei of atoms are split up into their elementary particles, the protons and the neutrons. This is a very important result, and we're going to use it again and again in what we say in this lecture. Now, can we possibly check that this has actually happened? Well, the answer is yes, we can. And it's one of the great stories of modern astronomy and cosmology. Because what we can do is to now start the universe at a very high temperature, put in the best nuclear physics we can, and then let the computer follow what happens to all the reactions. We therefore start with free protons and neutrons, and then we watch them combine when they come through down about a temperature of 1 billion degrees. What we're showing here is the protons and the neutrons, which are present in the very early universe. They combine to make deuterium. Then we add on another proton, and that then makes helium-3 with 2 protons and 1 neutron. And then 2 of these helium-3 nuclei combine together to make a helium-4 nucleus. And that is the process by which we make helium in the universe. Now, we've been working rather hard in this lecture so far, so let's have a bit of a party game. At home, we've got a game which we call the Helium Factory, and I've trained up some expert helium-4 makers for a bit of a party game. Would you like to come and help me? Good. Now, what my helpers here are going to do, they're going to carry out each stage of the chain of this nuclear reaction for making helium out of hydrogen. Now, we'll do it first very slowly, and we'll just run through this sequence. Okay, Zoe, shall we go? We'll make one helium atom. First of all, we join together the protons and the neutrons to make deuterium. Then we add on one proton to make helium-3. And then we wait until another helium-3 comes along. We remove a proton, and we then join them together to make one helium nucleus. Thank you very much. Beautifully done. Thank you. Now, this is the production line by which we make helium in the universe. We're going to set our production line really going. Ready, steady, go. Right. Now, here we go. There's deuterium gradually being building up, made into helium-3. We sometimes lose a proton here and there, but here we go. Faster, faster. There we are. We're almost getting the first of our next helium one done. There it is. It's made. Thank you. We've got 2 now. Good. Here they're going. The production's going. When we play this at home, we do much faster than this. It gets very boring after the 20,000th helium nucleus, but there we are. Thank you. There's another one. That's right. How are we getting on? Notice that the neutrons are all being gobbled up in this chain. Terrific. We've got one more. How well are we doing? Right. There we go. Dear me, look what's happening to all the neutrons. They're having a heart attack. Oh! Neutrons are lost. Good. Thank you very much, Zoe. That's fine. Good. There we are there. And are we going to make it? Terrific. That's great. Thank you very much. That's splendidly done. Thank you very much. Great. Well, they're really great helium builders, right? Now, the beautiful thing about that experiment, it's a great bit of fun, but what I gave them were exactly the right numbers of protons and neutrons that these reactions start off with in the hot Big Bang. We start off in proportion 12 neutrons and roughly 100 protons. And what you saw happening was that all the neutrons eventually got combined into helium-4 nuclei. And if you work out the sums, you'll see there's roughly about 23% of the mass is now converted into helium when we started off with neutrons and protons. And that's a wonderful result, because wherever we look in the universe, we see round about 23 or 24% of helium by mass. That has always been a terrible problem for cosmologists, because whenever helium is made in ordinary stars, it gets burned into heavier elements, and we could not understand why it was that the helium was so uniformly distributed throughout the universe. And here's the answer. The helium is all being cooked in the hot Big Bang. Now, let me show you what happens in slightly more detail. I'm going to show you the first 12 hours of the universe, and we're going to run the clocks forward in time following the nuclear reactions as they go on. Now, on this computer demonstration, what we've done is to show the mass fraction. That means the fraction by mass of different elements which are being cooked in the Big Bang. And it's a huge scale going from 1 here, 1,000th, 1 millionth, 1,000th millionth. And we've got here a clock measuring time in hours, minutes, and seconds. And we've got also a thermometer, which is keeping track of the temperature in billions of degrees Kelvin. Okay? From our physics, we know that we start off with roughly 1 neutron for every 10 hydrogen nuclei. That's the protons. And so we're now going to run through the first 12 hours of the universe, watching the temperature going down and the clock running. Shall we go? Let's go. Here we go. Now, very soon, we start to build up little bits of deuterium, little bits of helium-4, some tritium, helium-3 coming. 1 minute's passed. We're up to 2 minutes, and still we're building up these light elements. 3 minutes have passed, and now suddenly we see the neutrons beginning to be combined into the helium nuclei. We're also finding we're getting some deuterium built, as well as helium-3. And we're even getting some lithium built. We've now got to roughly the first hour in the universe. The temperature's continuing to decrease. and essentially everything's over. You'll see these curves are flattening out as we go later and later in this first 12 hours. The only thing that are dying are the neutrons. What's happening here is that they're simply decaying. They've got a half-life of only about 10 minutes, and so they are dying away in the universe. And here, after 12 hours, are the products of synthesis of elements in the Big Bang. Now you will notice that we've done much better than simply making helium. Here is the hydrogen and the helium, which we made through our production factory. But in addition, we've made some deuterium, we've made some helium-3, the isotope of helium, some tritium, and even some lithium. But they're made in very different proportions. Here's a representation of how much we've made. We've made this amount of hydrogen, we've made about this amount of helium-4, and then we've made tiny amounts of deuterium, a tiny amount of helium-3, and an infinitesimally small but very significant amount of lithium. Can you see that dot? Yes. Well, that's an exaggeration of how much lithium is made. Now, it's quite probable that indeed these elements were all cooked in the hot Big Bang. And in fact, if you've got a digital watch and with a lithium battery in it, then the lithium that's in there is probably coming out of the hot Big Bang. That's where the lithium was made. So this is another beautiful result, because you see, deuterium is another of the elements which is extremely difficult to make in the hot Big Bang, in stars. We cannot make deuterium in stars because as soon as deuterium is made, then it gets disintegrated by the very intense radiation inside the star. And so astronomers have never known how they could actually make even as much as 10 to the 1 part in 100,000 of the universe in the form of deuterium. But here is the answer. We can make the deuterium in the hot Big Bang. Now, this is very important because what it means is that we've now got 3 essentially independent reasons why we favor this hot Big Bang model. You see, we've got, first of all, the expansion of the universe. That suggests the universe started off very compact in the early stages. Secondly, we've got the microwave background radiation, which has got this perfect black body spectrum. It's got that spectrum because the whole of the matter of the universe was in equilibrium in the very hot early stages and has preserved its form since that time. And now we've got the abundance of the light elements. We can explain the origin of helium, helium-3, deuterium, and possibly even lithium by the one hot model of the universe, which we could not explain otherwise. And so that's why astronomers and cosmologists take the hot Big Bang very seriously indeed. It can explain these 3 totally independent observations by one single theory. But we get more. And that is that it turns out that deuterium is a remarkably sensitive measure of the density of ordinary matter in our universe. Now, you'll notice that when we ran our production factory for making helium, that all of the neutrons were absorbed into helium-4 nuclei. Now, suppose we had run a very low-density universe. Suppose that we'd separated out our manufacturers rather widely. Then what we would find would be that not all of the neutrons make it into helium-4 at the end, but we would get more deuterium left over in the middle stages. And this is a very important point. If we've got a very high-density universe, we get very little deuterium made. If we've got a low-density universe, then we leave quite a lot of deuterium behind. And so when we measure the present abundance of deuterium in the universe, we get a strong upper limit on the density of ordinary matter in the universe. Note how the argument goes. If the universe had indeed the critical density, we would destroy most of the deuterium that is trying to form in the universe. In fact that we see 1 part in 100,000 of deuterium in the universe tells us that the amount of ordinary matter in the universe cannot be more than about 1/10 of the critical density. That's a crucial point. You see, here is the critical density in our scales again. We know that the ordinary matter, the visible matter, is about a 50th of the critical density. But the amount which we are allowed from the hot Big Bang is only about 1/10 of the critical density. It's a very important result, because it means if we have to find matter in the universe to make it up to the critical density, it cannot be in the form of ordinary matter at all. This is why the early universe is so exciting for the particle physicists, because it means that we cannot make the whole of the critical density out of ordinary matter like the protons and neutrons that we were making here, but we may have to call upon exotic particles, the sorts of particles we don't know about yet in laboratory experiments. And they could consist of the whole range of these new ultra-weakly interacting particles predicted by the theories of particle physics. These have not been detected, but the theories suggest that at very high energies, very high temperatures, such as we find in the early universe, these sorts of particles may well exist. So it's a very exciting prospect that maybe if the universe really has the critical density, most of the mass may be in the form of these exotic particles. We don't know, but it is distinctly on the cards. Now let's go to our second great problem, and that concerns antimatter in the universe. Now, what is antimatter? Well, antimatter is just like ordinary matter, but it is essentially the mirror image of the ordinary matter. In other words, the charge is opposite. If you've got a positive proton, then there's a corresponding negative antiproton. If you've got negative electrons, there's a corresponding positive electrons. And we know that sorts of matter can be created in accelerator experiments. Here are a couple of examples of this happening. Now, when we come to think about these very high energies, it's often simpler to think of radiation in terms of particles rather than in terms of waves. So at very high energies, we can think of the radiation consisting of particles that we call photons. Now, here is an example from an accelerator experiment carried out in America, where a gamma ray has come in, collided with a nucleus, and produced a negative electron spiraling in this direction, and its antimatter partner, the positive electron or positron, circling round in this direction. Here's another example on the next slide of the same thing happening, where we've got a particle coming in here with very high energy, creating particles which move off in one direction, and their antiparticles, their mirror image particles, off in the other direction. Now, why is this a problem? Well, the reason is that in the early universe, we're going to get lots and lots of very high energy gamma rays. And they're going to be such high energy that they're able to produce protons and antiprotons when they collide with the protons in the universe. Now, this leads to a rather peculiar situation, because we can measure exactly the number of photons in the universe to the number of protons. All we've got to do is to count the number of photons in the microwave background and compare that with the number of protons in the universe. And it turns out to be a very big number, a number like 100 million or a billion. There are roughly 100 million or a billion photons for every proton in the universe. Now, when we go, therefore, back to the very early stages, these photons are going to create particle-antiparticle pairs. And the universe will be swamped by particles and antiparticles. But there must be a slight asymmetry so that we leave our matter universe now. Let's demonstrate that by a little graphic that we've produced here. We've produced a sort of game of cosmic snooker, which I want you to watch. Now, to run this program, I need an odd number somewhere between 10 and 20. Would people like to shout out some numbers between 10 and 20? Thank you, thank you, thank you, thank you. I heard someone say 15, so I will put 15 into this demonstration. And if we've got 15 particles, we're going to split them up into 8 particles and 7 antiparticles. They will collide, and when they collide, they will then produce photons, just the particles of radiation. So I will now set this up completely at random. I don't know what the result is going to be, but we'll set up this situation. The green particles are the protons, and the orange particles are the antiparticles. So let's run the program. Off we go in this game of cosmic snooker. Whenever the particles and antiparticles collide, you see they become photons. And we'll just let that program run for a little time. It's always difficult to get rid of the last particle. And you can see this is a very important result, because it tells us that if we see this, that we've only got one proton now relative to, say, 1 billion photons, then in the early universe, there must have been roughly 1,000,000,001 protons and 1 billion antiprotons. When the universe cools down, then the 1 billion protons annihilate with the 1 billion antiprotons, producing photons, and we're left with 1 proton left over, which becomes our universe. Has it gone yet? This is a wonderful program because it shows you what happens in real life. It's a statistical process. Eventually, we believe it will go away, but we've just got to keep on waiting. Eventually, we'll find that the proton and the antiproton, we've got a very persistent antiproton there, haven't we? So this is the problem. Why was it that there was this small asymmetry in the early universe? That there were particles and antiparticles, but a slight excess of particles relative to the antiparticles. We've done it. Great. That's right. There's our universe. Now let's go to our third big problem. The third big problem is, why is our universe, why does it look the same in all directions? Now, I'm going to illustrate this by a space-time diagram. And Bipin and his colleagues have produced a beautiful space-time diagram for me here. We looked at these in the first lecture, but let me go through it again. We've got time running up from the Big Bang here, right up to us here at the present time. This is our galaxy sitting here at the present. And these blue lines represent galaxies expanding away from the Big Bang. Now, we've shown by these brass lines here, light, the path of light rays. Remember, light only travels at a finite velocity, the speed of light. And so when we observe a distant galaxy, such as this one, we see it in the past, not as it is at the present time, which would be up here. What I want to do is to show you what happens when we look at regions very far away in the universe. Now, the big trouble is that things get rather complicated down here, so I'd like someone to come and help me to open up the universe a bit. Who would like to come and help me? Would you like to come? Right. What's your name? Sorry?
Shooter.
Right, Shooter. You come and help me. Now, what we're going to do is to pull the universe apart. Now, you hold that one. Don't pull yet until I tell you. And I'll take this one. And we're going to do a mathematical transformation to convert the Big Bang from a point into a straight line. Right, let's pull it. Right, here we go. Pull, 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 pull. Excellent. Thank you. We've straightened. That's done. Well, that's straightened out the universe a bit. You see what's happened is that we've simplified the whole business. We've now got galaxies running vertically up the diagram, and we've also straightened out the paths along which light travels. Now you can see what the problem is. That this galaxy here and this galaxy here, light travels to them along their own, what we call past light cones, from here and here. And this galaxy gets information from this bit in the past. But you can see that these two cones don't overlap. So there's no way that radiation could get from this galaxy to this galaxy in the time of the universe. So how on earth was it that this bit of universe knew that it had to be the same as that bit of universe? There isn't time in the available time in the universe to do it. The fourth problem we've already discussed in our previous lecture, and that is that how can we possibly make galaxies and the large-scale structure of the universe? And you'll remember that the summary of that lecture was that in the universe, the instability which could make galaxies, they grow so slowly that it's very difficult for us to make galaxies now unless we put in fluctuations, little irregularities in the universe to begin with. These are then the 4 great problems, and I've summarized them here on this chart. The 4 big problems of cosmology are, first of all, why is our universe so isotropic, as we've demonstrated here by this beautiful space-time diagram? Secondly, why is our universe so close to the critical density now? Thirdly, why is there this slight asymmetry between matter and antimatter in the early universe? And fourth, where are these fluctuations from which the galaxies formed? Now, there's a really major problem with classical cosmology. Because, you see, the only way that we can explain these features of the universe is to suppose that these features were built into the initial conditions. In other words, we have to say that the Big Bang had exactly these 4 properties in order to make the universe as we know it now. And that's very unsatisfactory scientifically, because it doesn't have any predictive power. We don't like to have to say, well, if you put in these particular initial conditions, we'll get what we are like now, because it's telling us nothing. We're only getting out of our universe what we put in at the beginning, and that is not scientific. Now, fortunately, over the last 10 years, there's been a realization that there is a way of solving some of these problems. Now, this is very recent physics, and in fact, it's physics that we're not at all familiar with in our everyday life at all, but these phenomena of this type, have been observed in very high-energy particle experiments. Indeed, in the early universe, we've got a very high-energy plasma indeed, at temperatures far above the highest which we can obtain in terrestrial accelerators. Now, I'm going to cut a very long story short and simplify it to its maximum degree. You see, in the model of the universe that we've built so far, it is constantly decelerating. Gravity is always pulling the matter together. But suppose instead the universe started expanding exponentially. You remember that what we mean by that is that in equal time intervals, the universe would expand by the same factor. So we would get very, very rapid expansion indeed in the very early stages. It's the complete opposite of what happens in our normal models. This is what is known as the inflationary universe. Most people don't like inflation, of course, but to the cosmologists, it can solve this major problem of what happens in the early universe. Let me show how we can solve the first 2 problems in this sort of model. First of all, why is it that the universe is the same everywhere? Well, it's very simple. All the universe that we can observe started within one very small volume, and then rather than expanding as our normal models do, it expands exponentially, so that the bits of universe expand very, very rapidly beyond the horizon where they can communicate information or radiation to each bit of the universe. And in that way, by having an exponential expansion, we can start with all of the universe very dense and end up looking the same in all directions now. How can we explain the fact that the universe is so close to its critical density? Well, again, we've got to look at the geometrical properties of the universe. Here on this demonstration, we're showing the bit of universe that we're interested in, and we're showing a very compact bit in which the geometry is very compact, its spherical geometry very closely tied together. Now what I'm going to do is to let that sphere expand exponentially beyond the region that we're interested in. So we'll just press return. You'll see that very rapidly that the sphere begins to expand about the box in which we're interested in, and you'll see that within that sphere the geometry is becoming more and more rectangular, more and more flat. And in fact, when the universe expands by an absolutely enormous factor, then however complicated the initial geometry, then it gets converted into almost exactly flat space through the exponential expansion. Then, when the universe switches over at the end of that period into the normal universe as we know it, we will end up with flat geometry. And now we go back to this close relationship between density and geometry. If we've got flat geometry, we must have the critical density of matter, and that explains why the universe can set off with almost exactly the critical density. Now, we don't quite know what the forces are which cause that exponential expansion, but we already know of forces very like it which are required in order to explain the properties of fundamental particles. And so we're optimistic that we can find physical forces which can cause that exponential expansion. It turns out that to solve the third problem, that matter and antimatter are not precisely symmetric. There are particle physics experiments in which we know that there is slight excess of matter as opposed to antimatter produced in certain decays. When we use that type of phenomenon and try to see what will come out of the early stages of the Big Bang, it turns out that we can explain to order of magnitude what we see in the universe. This asymmetry between matter and antimatter. Finally, what about the fluctuations? Well, when the universe changes from the exponential expansion to the normal universe, that corresponds to a phase change in the universe. And when that occurs, just as when we find water boiling or else ordinary water freezing, we can get fluctuations in the medium. And this may be the origin of the fluctuations from which galaxies formed. How seriously should we take this? Well, the inflationary universe looks very encouraging indeed. And we are hopeful that we will be able eventually to convert this idea into a real physical theory on the basis of elementary particle physics. You see, what's happening is that our early universe is becoming a laboratory in which we're trying to study not only particle physics, but the origin of the large-scale structure of the universe. This is one of the greatest adventures of modern science, in which we're reconciling the physics of the very large and the physics of the very small. I hope that some of you will help us on what is one of the greatest adventures in cosmology and particle physics. Thank you very much.